Okay, change of variables, 16.7. So, what is this section about? This section is about like weird substitution. Well, actually, I don't know if you ever wondered why did you do the U substitution back in Calc 1, or what's really the idea behind, for example, you were asked to evaluate the integral of 2 root of 2x dx from 0 to 1. Ultimately, that's going to give us the area under that curve. All right? However, well, they told you about our U substitution to make the problem a lot easier. And then, well, the thing is here, if we do the U substitution, U equals to x plus 1, du equals to dx. And actually, well, we have the 2 and the dx, so that stands for the du part, and this is simply square root of u. And we also change the limits of integration. So u of 0 and u of 1. So in this case, 2 times 0 plus 1 equals 1, and 2 times 1 plus 1, that equals to 3. So that's why the new limits are from 1 to 3. Well, so this is what's going on, and well, when for those of you who took my calculus 2 class, whether in the summer or last semester, when we were doing this U substitution, I always mentioned, oh, we're going to send the integral from the world of x to the world of u. Right? So that's essentially what we're doing. So here we are twisting the shape. Actually, well, we are magnifying the x and reducing the y, or the height, if you will. So this U substitution is a linear transformation. Those of you who are in linear algebra, have you been talking about linear transformations already? The kernel of the transformation, and closure and all that about transformations and transition matrices. That's to do a change of bases. So
we're on that right now.
So that's basically what we're doing here. So when we're doing a U substitution, we're doing in a way like the transition matrix to go from the world of x to the world of u. And well, the advantage of going to another world is to make the problem a lot easier to evaluate, to compute, rather than this madness here, right? So that's why we do that, right? Well, so, and in general, so here's the picture of what that transformation is. So it turns out that we're going to do these transformations, or these U substitutions, but we're going to do this time for more than one variable. All right, so we're not going to do separate. Actually, we're going to do the whole thing together. You'll see how it's going to work. So, over here, do you see this? What's delta x here? 1. What's delta x here, or delta u rather? So, what happened to go from the world of x to the world of u? We had to multiply the delta x by 2. All right? So this number, which is the correction factor, if you will, it's given by what we are going to call the Jacobian determinant, or simply we call it the Jacobian. And well, so in this case, again, we want to go from one world to another world, and well, the substitutions, well, they're going to be given for us. So that's a good thing. We don't have to figure out a transformation on our own until we find the one that best suits the problem that we're solving well. So in this case, so if we consider the transformation, so that is, we want to go from x, y, to another world that we're going to call it u and v instead. So these x and y, which are going to be given in terms of u and v, they have to have continuous partial derivatives with respect to u and with respect to v. And we compute this determinant. Well, you might have seen the determinant. You know the determinant, a, b, c, d. That's a times d minus b times c. Well, in this case, these are going to be partial derivatives that we will have to compute. All right, so let's see. for example. So we have an integral, f of x, the double integral of f of x y dA. And again, that dA can be either dy dx or dx dy, depending on what's your preference, or depending on what it's easier, given that the region is vertically simple or horizontally simple. So in some situations, that's why we have to change the order of the double integration. Well, so you might remember when we change coordinates, you might recall from rectangular to polar, for example. And that's actually the exercise that we're going to do. Of course, so we are in a set where in this case is the rectangular set. That's the double integral over the region R of some function. Well, let's just call it dA for area and well, this is actually dy dx. All right. So that's our region R. And well, to go from the world of xy, from the rectangular world to the polar world, which we will describe with a different letter, a letter S. Well, we're going to go from dy dx to dr d theta. However, in the same way that we did the u substitution right here to go from dx to du, that du needs a correction factor or a magnifier or a reducer. Well, in this case it's a magnifier, which is a factor of 2. In polar coordinates we needed a magnifier. What was that magnifier? R, right? Well, we did the derivation or the deduction using geometry, taking a little piece of a sector of a circle and finding a delta R. So, and we multiply that area. We got that area by multiplying that delta R times the arc length that it's subtended between the two rays, which is delta theta times the radius. So that's where the R came from geometrically. When we went to, and this is going to become circular coordinates, right? We go from square to circle. In a similar way, so for the triple integral, for which we went from dc dy dx to d rho d phi d theta, we needed a correction factor of rho squared sine phi. Well, we got that geometrically by taking a slice of a spherical box, all right? And we define the delta radius, the delta along the equator of the sphere, and a delta going up to the pole, all right? And we put everything together by just multiplying the dimensions. Well, we're not going to do that whole thing again. So this time we're going to take a different approach to get the transformation from rectangular to polar. All right. So, well, let's number one recall the formulas to transform, to go from, or that relate polar and rectangular. So x is r cosine theta and y equals r sine theta. These are the formula that we have been using since calculus 2, right? Well, so we need to compute the Jacobian. So the Jacobian that is the correction factor to go from xy to r theta, will be the determinant of 4 partial derivatives that we are going to take here. So that is the partial derivative of x with respect r, the partial derivative of y with respect r, also the partial derivative with respect x, the partial derivative of x with respect theta, and the partial derivative of y with respect theta. Alright, so let's take those partial derivatives. Well, so we need to take the partial derivative of x with respect to the radius. Well, the derivative of r is 1. That's going to leave us with cosine, right? And well, let's evaluate the derivative of x with respect to the angle. This time the derivative of cosine theta is in that negative sign times r. That's going to give us negative sine theta. And for the second row, the partial derivative of y with respect r, well, that's the derivative of r is 1 times sine, so that's going to be sine. And the partial of y with respect theta, that's r cosine theta. So let's evaluate this 2 by 2 determinant by multiplying the elements along the main diagonal and subtract the product on the secondary diagonal. So this will be cosine times r cosine. Isn't that going to be r cosine squared theta? And then minus negative r sine times sine, which is r sine squared theta. Well, that turns into a positive. That's r cosine squared theta plus r sine squared theta. Factor out the r. That's cosine squared plus sine squared. But well, this is a very well-known identity, which is just a 1 times r, that's simply r, alright? And that's where the correction factor to go from dy dx to dr d theta is coming from. So that's another way to derive this using the Jacobian determinant. All right, so let's go about one example. So sketch the region. So in this case, they're just asking us to sketch the region and set up the integral, not to compute the integral. Sketch the region R in the xy plane given y greater than 0, but greater than or equal to 0, and less than or equal 1, the square root of 1 minus x squared. Sketch the corresponding region in S, which is in the r theta plane. So we're going to do the two regions, the region in the xy world and the region in the r theta world. All right. So what is this telling us? Well, this is really y equals 1 minus x squared, which is the upper part of a circle, right? That's the upper semicircle in this case. All right. Let's sketch R. So this is R. And well, in this case, so notice this would be the entire upper semicircle. However, this X, I remember I had more conditions here. So here, I needed to mention that X is varying between 0 and 1. All right. So that's the circular region and R. However, careful, because this upper semicircle is telling us that X is varying between -1 and 1. However, what's the condition here? The condition is that it's only varying between 0 and 1. So this is what we have to do. So we would have to just get only the part of the quarter of the circle that lies in the first quadrant. So that's going to be this area right here. All right. And well, so that's a sketch in R. I mean in the set R, which is the xy plane. Now here, the circle, this is telling us that R is varying between 0, so from the origin, and well, in this case, it's telling us this is the unit circle. And because we are only looking at the first quadrant, that is from 0, the lower angle will be 0 degrees, or well, 0 radians. And in this case, it's going to go only up to pi/2. All right? Only pi/2. So let's sketch the region in the corresponding, in the new set S. So we're going to go from R equals to 1 to theta equals to pi/2. And this will create a rectangle. Or a square, if you will. So the idea is that it's easier to integrate over a square than integrating over a circle. All right. So we are twisting the regional world of the regional region into something. Well, yes, the process is weird, if you will. However, it would do that for good to evaluate an integral in an easier way, right? So that's going to be our region in the xy plane, and then in the r theta plane. All right, so that means that we're going to go, if we set up the integral, without limits, we go from r dA equals double integral of s dr d theta. But well, in this case we would have needed to calculate the Jacobian, but we already got it from the previous part. That's just r. All right, that'll give us the area. So calculate the double integral over the xy plane. That's fine if you want to calculate it like that. You would have to do most likely a trigonometric substitution from Calc 2, right? Instead of just evaluating r dr d theta, I think it's just going to be very, very straightforward. So that's the advantage of having this kind of substitutions. All right. Well, so that's one example to connect what we did back in polar coordinates versus this with this introduction to coming up with this new substitution. But let's generalize the process here. And we have a sequence of steps right here. So, since this is just a little intro about the substitutions, we're going to limit ourselves to double integrals, all right? Because if we did triple integrals, then we would have to evaluate not a 2x2 determinant. We would have to evaluate a 3x3 determinant, right? Remember the cross product? With numbers it's fine, but if it involves expressions of x and y or other variables, it's doable, but it's going to take forever. Like, for example, the derivation for spherical coordinates, we can do it using the Jacobian, but in this case it would be a Jacobian of a 3x3, not a 2x2. So let's look at the process. Number one, determine the appropriate u and v substitutions, and that's always given. All right, you don't have to figure it out. Sketch the original region of integration in the regional world, which is what we call the world of R, which is usually the xy plane, and then determine and sketch the new region S in the uv plane, that is the transformed world. To do this, we need to express u and v as functions of the original world, that is of x and y. All right, and then we're going to use these relations and sketch to help find the limits of integration for the new integrals with respect u and v. Now that we have all those x's and all the x and y in terms of u and v, we need to compute the Jacobian to find out what the correction factor is, change the variables, and evaluate the new integral. So let's look at one example so you can see why do we do this. Okay, so number one, evaluate this double integral, which looks really simple. The integral of 4x. What could be hard about it? General power rule and the like. However, the region over we are going to evaluate this integral, you'll see what's going to happen here. Well, so let's sketch. So we're going to go 1, 2, 3, 4, 5, 3, 1, 2, 3. So the origin 0, 0, the point 2, 2, the point 4, 0, and the point 2, -2. So this is essentially a square tilted 45 degrees, all right, like a diamond, if you will. Now check this out. Is this region vertically simple? Is it horizontally simple? In fact, okay, let's do some label just for, so this is, let's call this y1. Whoops. No, I needed the other eraser. Okay. So this is y1. Actually, if you want to write this on the back of your page, y2, y3, and y4. So there's actually 4 equations of lines involved in here, right? In order to sort of determine, to sort of turn it into vertically simple, it would involve splitting into 2. So over here, before the split, here is vertically simple, isn't it? And then after the split, using a different color, it's also vertically simple. However, the area right here, the double integral over r for x dA, this would be the double integral between, okay, let's see, 0 to 2, for example, and in this case involves y2 and y1 for x dA. Let's call it dy dx, yes, dy dx. Plus the second part of the integration would involve to go from 2 to 4 and y, so in this case y4 below and y3 above for x dy dx. Do you want to evaluate 2 double integrals? This is what we would have done without knowing this Jacobian substitute, like the Jacobian determinant to perform a substitution, not a substitution, yes, a change of variables. So fortunately we have this, so we don't have to do all this. Okay. So what are we going to do? Well, so number 1, so we got the substitutions. Let me erase all this. Well, actually, let me draw the picture again. I think it will be shorter. So, that's our region. So number 1, use the substitutions. Well, for the substitutions, we got x equals u plus v and y equals u minus v. Okay, so this is what we need to do, and this is usually the tricky part. Rewrite u and v in terms of x and y. We have the reverse for now. We have x and y in terms of u and v. So this is what we're going to do. So I'm going to solve for u on the first equation, u equals x minus v, and I'm going to solve for v on the second equation. So that's going to be v equals to u minus y. Okay. So right here I'm going to substitute this v right here, which is u minus y. I'm going to substitute here. U equals to x minus v, which is this quantity. Actually, let me highlight it so you can see what it's going to be. And that's going to be u minus y. So distributing the negative sign, that's u equals to x minus u plus y. Well, moving the u to the right hand side, that's going to give us a 2u equals to x plus y. And solving for u, we get u in terms of x and y, which is one of our first parts of our main rule. Now we need to do the same for v. Well, so in this case, notice we already have this solved for v, and we also have this solved for u. So what I'm going to do here is this u, which is in terms of x and y, plug it in here, and v equals to u, which is x plus y over 2 minus y. And simplify this, that's v equals to x over 2 plus y over 2 minus y over 2. And well, simplifying, oh wait, no, not y over 2, minus y simply. So 1/2 minus 1, isn't that negative 1/2? So that's going to be v equals to x minus y, the whole thing over 2. So we got our u and v in terms of x and y. All right. So let's see, what would be next? So, all right, what did we get over here? The x. Oh, got it. And that's because we're going to need this u and this v to substitute on the original integral here, because in the same way that we used, what did we use? X in terms of r and theta and y in terms of r and theta, so we're essentially doing the same here. All right. So number one, let's sketch the region. So we're gonna go from the world. This is the region R. We're gonna go towards the region S, and we will sketch that in a second. Well, actually, we use these relations here to find the equivalent points that come from the world of X to those in the world of Y. All right, so I'm gonna make a table on the left side of on the right side. So that is X, Y, U, V. So I'm gonna list the order pairs: 0, 0, 2, 2, 4, 0, and 2, negative 2. And u and v, well, are going to be the corresponding. Okay, so let's look at the origin, 0, 0. So in this case, 0, 0, plug it in u, so 0 plus 0, that's going to be, 0, 0 over 2, that's going to be 0. Let's look at the v coordinate. 0 minus 0, it's also 0. 0 over 2 is 0. So the point 0, 0, it's the same in the world of R and in the world of S. Let's look at the point 2, 2. So here it's going to be 2 plus 2, which is 4. Divide that by 2. That's a 2. Let's look at the v coordinate. 2 minus 2, that's 0. 0 over 2, that's a 0. The point 4, 0. So 4 plus 0, that's 4. Over 2, that's a 2. And 4 minus 0, that's 4. Okay? Oh, wait a minute. 4 over 2, which is 2. And lastly, 2 plus negative 2, that's a 0. Over 2, which is 0. And 2 minus negative 2, careful there, because that turns into an addition. That's a 4, and 4 over 2 is 2. So we're going to plot these 4 points in the new Cartesian plane that we created here. So, and check what's going to happen. So that's going to be the point 0, 0, the point 2, 0, the point 2, 2, and the point 0, 2. What did we get? Isn't that a region a lot easier to integrate over? Alright? It's both vertically simple and horizontally simple instead of that diamond or that 45-degree rectangle. So now we need to find the Jacobian for which is the operation that rotates this 45-degree angle square. In the same way, like those of you who are in linear algebra, when you're multiplying some vector times the transition matrix, that's to find the equivalent of that vector in the original set, and to find the equivalent onto the other set. So, well, you have them, and actually you find a transition matrix to go back and forth, because that means you will have to even find an inverse of that transition matrix, so you can also go back to the original. So you can transfer a vector from the new world back to the old world, right? To go back and forth. All right, so it's something similar here. In fact, it's what we're doing. It's a linear transformation. It's a change of basis, if you will, but in this case, to apply to evaluate integrals over easier regions like this square. So let's go about it. Number 3. Okay, so this was number 2 to sketch. Number 3, find the Jacobian. So the Jacobian over the world u and v will be the partial of x with respect u, the partial of x with respect v, the partial of y with respect u, the partial of y with respect to v. And well, let's find the partials from here. Okay, what's the derivative of x with respect to u? The derivative of u, isn't that 1? So that's 1. The derivative of x with respect to v, so the partial derivative of x with respect to v, well, the derivative of v is also 1. And then the derivative of y, now let's look at the second equation. The second row is for the derivatives with respect, the derivatives of y. So the derivative with respect to u, it's also 1, but the derivative with respect to v, that's a negative 1. All right? And well, in this case, so that's going to give us 1 times the negative 1, which is negative 1 minus 1 times 1, which is 1, and the result is negative 2. However, be careful with the result, because what are we doing? We're finding the area, or well, technically it would be the volume, because we have a double integral with an f of x in the integrand, so that represents volume. So if we multiply by that correction factor, by the Jacobian, which is negative, that's going to give us a negative volume. However, again, let's go back to the definition of the Jacobian, or rather the integral. Notice in this case we take the absolute value of the Jacobian. So if you get something negative, turn it into a positive. All right? So, well, let's set up our integral. And well, that's the double integral over the region R for x dA. That's the new integral in the world of S, but that 4 remains there, but we're no longer going to write x. We're going to write the expression of x in terms of u and v, in v, which is this one right here, u plus v. Let me highlight that. So this x equals to u and v comes from the given transformation, and that's given, all right? That's not something you have to figure out. What you need to figure out is the new variables in terms of the original variables, which is by basically doing these substitutions that we did. And well, in this case, we want to go from the world of dy dx to the world of du dv. But the correction factor right here would be 2. In fact, so I forgot to take the absolute value. All right, which is, let me also highlight that part. A different color. This one right here. And that'll become 8 times. So 4 times 2, that makes an 8 outside of the double integral. And in this case, well, let's look at the limits with respect to x. Doesn't x vary between 0 and 2? Well, not x, actually it's u and v. 0 and 2 and 0 and 2 for v. And that's u plus v du dv. All right? And well, this integral after some steps should give you 64. Right? The most important part again is the setup. I mean, doing this integral gonna be kind of tedious to do all this repeatedly, right? So